Phoenix, Arizona, 43.6 degrees on the design day. And somewhere in that heat, a data center has to throw away the waste heat of tens of thousands of servers using nothing but the air outside. It cannot, and here is the part that should bother you. Making the cooler 10 times bigger does not fix it. The water still comes out at 49 degrees, 4 degrees too warm for the machines it is meant to cool. I am Dr. Engineer Lucien Wolf Penlap, and this is AIntelligence. In the next 13 minutes, I will show you the one temperature that decides whether a data center can be built in a city at all. It is not the one on the thermometer outside. It has a different name, it behaves differently, and almost nobody outside a cooling office ever mentions it. 4 cities: Phoenix, Cape Town, Nairobi, Lagos. 4 ways of throwing heat at the sky. 16 answers. And every one of them measured from published design data with the station number on screen every time. And here is what you are staying for. There is a version of this cooler, there is AIntelligence, that would work in Phoenix. It is infinitely large and nobody sells it. There is Akabota Akandwajinai Rafi ducting. And there is one day a year when even that one fails. Before the end, I will show you which day and by exactly how much. If you want more engineering done this way, measured, sourced, and willing to say when it got something wrong, like genuinely helps. And if you find a figure in here that is wrong, put it in the comments. I correct on screen. There is already one correction in this episode, and I will show you that too. So, 2 temperatures live in any air. The one a thermometer shows, dry bulb. And the one you get if you wrap that same thermometer in a wet sock and blow air across it, wet bulb. The wet one always reads lower. Water leaving the sock carries heat away with it, about 2,500 joules for every gram that evaporates, taken straight out of the glass. How much lower depends on how thirsty the air already is. Dry air drinks a lot and the reading falls a long way. Air that is already saturated drinks nothing, and the 2 readings meet. The gap between them is called the depression, and it is the most useful number in cooling because wet bulb is a floor. No evaporative device of any size, of any design, makes water colder than the wet bulb of the air entering it, not an engineering limit. Thermodynamics. Hold on to the shape of that sentence because we are going to meet its opposite in a minute. A limit that is an engineering one, and which behaves completely differently. In practice, you never reach the floor. You stop short of it. And the distance you stop short is the approach. An open cooling tower, 3 to 6 Kelvin above wet bulb. Below about 2.8, the economics collapse. No manufacturer will guarantee it. A closed circuit cooler, 2.8 to 3.9 or greater. That is a floor with no ceiling attached. An adiabatic cooler, measured pad effectiveness of 72 to 78% against the 90 the suppliers advertise. And a dry cooler does not chase wet bulb at all. It chases dry bulb. And the lowest figure anyone publishes is 5.6. One thing about those 4 numbers, and I want it on the record, not one of them comes from a standard. They are manufacturer application data and industry practice. The standards tell you how to measure an approach. What it costs you in a real machine is somebody's product literature. I will mark them differently on screen for the rest of this video. And here is the piece almost every explanation drops. Between the tower and the room, there is usually a plate heat exchanger with an approach of its own, around 3 Kelvin. Add a recirculation allowance, roughly half a Kelvin more, 3.5 Kelvin, gone before the water reaches a single server. That does not sound like much. Watch what it does. 4 cities: Phoenix, Cape Town, Nairobi, Lagos. Design conditions, ASHRAE 2021. The 0.4% percentile, the condition exceeded about 35 hours in an average year. Dry bulb first. Phoenix 43.6, Lagos 34.8. Phoenix is 8.8 degrees hotter. Now wet bulb. Phoenix 24.2, Lagos 28.3. The order has flipped. On the number that actually governs evaporative cooling, the hotter city is 4 degrees better off. That is the whole reason this video exists. Everyone knows Phoenix is hot. Almost nobody in the conversation about where to build data centers is looking at the second thermometer. One caution, and it is on every plate for a reason. Cape Town International is World Meteorological Organization 688160. 688170 is Cape Town Portnet, a different station that returns the identical wet bulb. One digit, and the answer looks right either way. Station number and elevation stay in frame. A note on vintage too. There is a 2025 edition of this dataset. I am using 2021 because it is the one I can check against the file ASHRAE publishes openly, 22 fields out of 22. In the newer edition, these 4 wet bulbs move by at most 0.3 of a degree, and every comparison in this video survives. 4 ways to throw heat at the sky. An open tower drops water through moving air. Best approach, cheapest per kilowatt, and the water is open to the atmosphere, so it fouls. It needs treatment, and it evaporates away. A closed circuit cooler puts the processed water inside a coil and sprays the outside of it. You keep the water clean, and here is what nobody says out loud. You have also deleted the plate heat exchanger, and with it 3 Kelvin. That deletion is worth about as much as the best tower upgrade on the market, except you get it by removing a component instead of buying one. An adiabatic cooler pre-wets the incoming air, dropping it partway toward wet bulb before it reaches a dry coil. Pads are advertised at 90% effectiveness, measured 72 to 78. And a dry cooler uses no water at all, which means it is not chasing wet bulb, it is chasing dry bulb and getting no closer than 5.6. One more thing before the numbers, because otherwise the top comment writes itself, and it is right. All of this is about cooling without a chiller. Put a mechanical chiller in and you can make cold water in any city on earth. You just pay for it in electricity every hour, forever. Phoenix has data centers and they run chillers. What this video is measuring is the temperature above which you have to. ASHRAE's thermal guidelines class liquid-cooled equipment by the warmest water it will accept. W27 wants water no warmer than 27 degrees. W45 will take 45. So the question stops being how cold can I get the water and becomes which class will this city support with this machine without a chiller? 16 combinations. And I am going to draw everyone as a band, not a line, because the approach figures underneath are ranges. 5 of the 16 straddle a class boundary outright. 4 more are floors with no ceiling at all. WS W20 have. 9 of 16 are not a single class, and pretending otherwise would invent precision I do not have. Open tower, Nairobi W27 to W32, Cape Town W32, and it cannot reach W27 because that would need an approach under 2.5 Kelvin, below the floor where anyone will quote you. Nairobi, Mahab, Cape Town is where you want the tower nobody sells. Lagos, W40, and Phoenix, W32 to W40, reaching W32 on an entirely ordinary tower, which should tell you something. On the wet side, Phoenix is unremarkable. Closed circuit does better everywhere because you have deleted the heat exchanger. Nairobi and Cape Town to W27, Phoenix to W32, Lagos straddling W32. Dry coolers. All 4 of these are floors, not classes. This class or worse with no ceiling. Nairobi, W40 or worse. Lagos lands at 40.4 degrees. That is 0.4 of a degree over the W40 ceiling, which is inside the rounding of every number that went into it. I am calling that a tie. And Phoenix, W+. That is a real category in ASHRAE's guideline. It means water warmer than 45 degrees, and almost nothing in a data center will take it. 3 things fall out of that plate. 1, the ranking depends entirely on the architecture. Go evaporative and Lagos is worst. Go dry and Phoenix is worse by 8.8 degrees, the same 8.8 from chapter 3, arriving from the other direction. Same 4 cities, opposite answers. Anyone who calls a city hard to cool without naming the machine has not finished the sentence. 2, closed circuit wins in all 4. Not because the coil is clever, because deleting the plate heat exchanger deletes about 3 Kelvin. The best tower upgrade you can buy, going from a 6 Kelvin approach down to 3, gets you 3 Kelvin as well. Same price. One of them you purchase, the other you get by removing a component. 3, and this is the one, Phoenix on dry cooling. Design dry bulb, 43.6. Add the smallest approach anybody publishes, 5.6, and you are at 49. Now, a bigger cooler does narrow the approach. Push it to infinity and the approach goes to 0, and you land on the dry bulb itself, 43.6. That clears W45 by 1.4 degrees. So at the design hour, the physics permits it and the catalog does not. No dry cooler on sale lands anywhere in that gap. The smallest approach you can buy is 4 times the margin you have. That is a market wall, not a physical one. Except 43.6 is the 0.4% figure. It is exceeded about 35 hours a year. ASHRAE also publishes the extreme annual maximum. And for Phoenix, that is 46.0 degrees. The infinitely large cooler, the one that does not exist, the one with zero approach, delivers 46-degree water on the hottest day of an ordinary year. It misses W45 by a full Kelvin, not the catalog, the air. On that day, the wall is real, and no cooler you can buy or imagine gets over it. One more thing, and it is the part an operator should worry about. The W classes are not evenly spaced and they are not fixed. ASHRAE's guidance notes that the capability to run at the warm end, W45, is not spreading the way it was expected to, and that a good deal of new liquid-cooled equipment is being specified back at W32 and W27 because chip junction limits have not moved as fast as chip power has. I am quoting that carefully because it is an observation about the equipment market, not a physical law. But the direction matters. The line you have to clear may be coming down while the heat you are throwing at it goes up. And notice what that does to Phoenix. At W45, its dry cooler is 1.4 degrees short. At W32, it is 17 degrees short. The same city, the same air, a very different problem. What does missing a class actually cost? Not an outage, derating. You do not lose the site. You lose the top of its capacity during the hours the design condition is exceeded. And because that is a percentile of the whole year, those hours cluster in the hottest weeks, which is also when the grid is tightest and power costs the most. The penalty lands exactly where it hurts. Or you fit a chiller and pay for it in electricity for 20 years. And it changes site selection in a way the announcements never mention. A city can have cheap land, good fiber, and a grid connection, and still be the wrong place because of a column in a table almost nobody outside HVAC opens. Phoenix is not a bad place for a data center. It is a bad place for a dry one. Everything from here is speculation, and it is marked as such. Every architecture in this video throws heat at the sky. That is the shared assumption underneath all of it, that rejection means disposal. The wall only exists because the destination is the atmosphere. Send the heat somewhere that wants it. A district loop, a greenhouse, an absorption chiller, any process that will take 60-degree water. And the wet bulb outside stops being the binding constraint. Not a new idea. What is new is that the wall is now close enough in enough places that the arithmetic might finally favor it. 10 times bigger, still 49 degrees. Because between the cooler that works and the coolers that exist, there are 4.2 degrees that nobody sells. Every figure here, station, period of record, and whether it came from a standard or a catalog, is in the description with the date I measured it. If one is wrong, tell me, and I will correct it on screen in the next episode.